Makiama Anjana. And I learned just those couple of words of Romanian. Unfortunately, that's 90% of my Romanian right there. So I'm from the US. I live in San Francisco, and I work for a company called Mapbox. I'm engineering, learning, and development lead there. Mapbox makes APIs and SDKs for developers like you all to make really awesome location-based apps. Happy to chat about it after the talk, but not really going to get into what we do there today. I also just really quickly want to give a shout out to some tech communities that I really love, and without which I wouldn't be standing here talking to all of you beautiful people. One is called the Recursive Center. It's a free, self-directed programming retreat in New York City. It's basically a place where you can go for 6 weeks or 3 months and just get better at programming, whatever that means for you. It's awesome. Check it out, recurse.com. Another is a fabulous initiative called Outreachy that aims to get more women and underrepresented minorities involved in open source by offering paid remote internships at open source organizations and projects. It's really fantastic. If you know anybody looking for an internship, or if you're looking for an internship yourself and you're a member of an underrepresented group in tech, check out outreachy.org. They work with a lot of different organizations and a lot of different open source projects. One of the organizations they work closely with is Mozilla. I was lucky enough to intern with Mozilla a couple of years ago, and I still keep in touch with the Mozilla community through a group called Tech Speakers, Moz Tech Speakers. Shout out to tech speakers who are here. So you can find us. Often you'll see us in those blue and yellow heart logos around at conferences around the world. So yeah, feel free to say hi. And I'm happy to chat about any of these things. If you're curious, come find me after the talk. So another important thing to know about me is I wasn't always a programmer. In university, I didn't study computers. I didn't get into it until later in life. And at university, I studied philosophy. And so this maybe is why, when I started to learn about programming, I really loved thinking about abstractions and kind of the mental models that we use to reason about code and think about how our programs work. So I really love programming paradigms. And if you want to nerd out with me on all the different paradigms and kind of what we can learn from all of them, check out a talk I have called Programming Across Paradigms. In this talk, we're not going to get into like all of the different possibilities. I want to talk about 2 paradigms in particular that are sort of star-crossed in the sense. So they're almost like these 2 completely different worlds that they represent, and you might think that they could never come together. So they're sort of like star-crossed lovers in that way. And the paradigms I'm talking about are iteration and recursion. Now, you might not think of these as programming paradigms. They're not usually referred to as kind of major programming paradigms. Iteration is associated with the iterative programming paradigm, the imperative programming paradigm, and recursion is associated with functional programming. But they're sort of like sub-paradigms of each of those because they're mental models that help us think and reason and understand about how we want to solve problems by executing a same piece of code multiple times. And so they offer kind of different approaches to how we might do that. So iteration, as we said, is sort of part of this imperative paradigm where we're telling the computer, do this and then do that. And so our programs are made up of commands, kind of instructions. And in iterative code, we're going to be executing the same code, the same chunk of code multiple times in repetitive loops using like for or while. And as we go through those loops, we maintain state. Between different runs through the loop, we remember how variables are changing. So maybe we have a counter that we're incrementing, or maybe we have an array that we're pushing things onto. And so it's a stateful paradigm. And I'm a big fan of using kind of mental association. I like to kind of associate things in my head to help me remember them better and understand them better. And I also love movies. And so when I think of iteration, I can't help but think of a movie called Groundhog Day. Has anybody seen this? Yeah, okay, a few people. So if you haven't seen this, in Groundhog Day, which came out in the 90s, it's got Bill Murray, awesome comedian, if you ask me. His character is trapped in the same day. He's like reliving the same day over and over. Every morning he wakes up and the same stuff happens throughout the day, and he goes to sleep and then it all starts over again the next day. So he's stuck in this kind of like infinite while loop. But it's also stateful because he can also remember that he's been there before, and he can learn things. Like he can take piano lessons and like get really good at piano, even though he only has one day. So I think Groundhog Day is a really great example of like how iteration works. Okay, so that's iteration. What about recursion? So as I said, recursion is associated with the functional programming paradigm, where instead of imperative commands, we are thinking about programs in terms of functions that take inputs and return outputs. And our programs are composed of multiple functions that we can put together to do increasingly complex things. So in recursion, when we take the same chunk of code and run it multiple times, instead of looping, like in iteration, we're making references to ourselves. So maybe we have a function that calls itself, and then that function can call itself again, and so on and so forth. So we're kind of like building this kind of Russian doll scenario where we're nesting calls to functions. And instead of having this stateful sort of memory of values changing over time that we have in iteration, we've got a more stateless approach. So each function call doesn't really need to know anything about like how many times that function has been called before. All it needs to know is what are my inputs and what do I need to do to return my output. Now there's also a movie that recursion reminds me of. Can anybody guess what it is? Yeah, of course. It's Inception, right? This is like the perfect example of how recursion works. So has everybody seen Inception? Like half of people. Okay, if you haven't, basically Leonardo DiCaprio and his friends, they can go into dreams, and then inside a dream they can like fall asleep again and go into another dream inside that dream, and then they can go even further and fall into a dream within a dream within a dream, and so on and so forth. And when they wake up, they go up to the previous one, and so on and so forth. And yeah, they also don't know, right? They don't remember whether they're awake or asleep, or it's hard to tell, so he has to carry around a little top that like somehow helps him understand whether he's dreaming or not. Anyway, go watch the movie. It's pretty good. So is Groundhog Day. Very different. But this is the point, right? These are two very different paradigms. They have something in common in the sense that they're both ways that we can execute code repeatedly, and they're ways that we can solve bigger problems by breaking them down into smaller chunks. But they're kind of often seen as being sort of in opposition. There's this tension between them. Now, they're both equally valid. We might say that they're two paradigms alike in dignity. They're both totally valid approaches for going about writing code. Now, some people might prefer one or the other, and often these arguments, which if you go online and read forums and Hacker News and whatever, like people argue about it infinitely, it often comes down to questions of efficiency. So let's talk about efficiency. A lot of people will say, well, iterative code is better because it runs more efficiently. It's more performant. Well, okay, but let's think about what we mean when we say efficiency. There's a really great quote from a programmer named Jonathan Blow. He's an indie game developer. He made the game Braid. I don't know if anybody's played it. Anyway, he's got this talk that my current boss, Young Han, pointed out to me that has this really nice, he puts it a really nice way of how we can think about efficiency when we talk about humans, all of us, writing code. So he says you might optimize for speed in your programs. You might optimize for space. But there's a third thing you might want to optimize for. And that's years of your life required per program implementation, right? We are humans. Our lives are not infinite. And so he says this is more important than those other things, or at least equally important. And I think this, I totally agree. I think this is a great way of putting it. I think when we talk about efficiency, we need to really distinguish between machine efficiency, so what's efficient for the computer when it runs our code in terms of its resources, time, space, and what's efficient for humans, us, when we write the code, or when we read it, or when we try to maintain it. And so when we talk about efficiency, I think we really need to be clear about which one we have in mind. And these two paradigms, and I'm using the colors and the fonts to kind of echo this, these two paradigms are often associated with one of these types of efficiency. So iteration is often seen as more machine efficient, and recursion, a lot of people find more kind of elegant, more intuitive, once you kind of wrap your head around how recursion works. And so some people say it's more human efficient. Now, the setting for all of this we're talking about these two paradigms in is, of course, JavaScript, because we're here at a JavaScript conference. And so it is in fair JavaScript where we lay our scene today of these two paradigms alike in dignity. And yes, For any English literature buffs in the audience, these are the opening lines of William Shakespeare's Romeo and Juliet, two households both alike in dignity in fair Verona where we lay our scene. Anyway, so now I've quoted Shakespeare in a tech talk, achievement unlocked, and I've also made 2 Leonardo DiCaprio movie references in the first 10 minutes of a talk, another achievement unlocked. Yes. But this is, I thought this is sort of apt because a lot of people, and again, on the internet, you see people arguing about this, they sort of had this idea like, there can be only one, and everybody's got their guns pointed at each other, and everybody's got an opinion, like, no, I will only write recursive code, or like, oh, recursive code is so inefficient, I would never do that. I don't think it has to be that way. I think this story has a happy ending. And I think that these two, like, sort of these paradigms that we think of as being opposed to one another, they can actually really complement each other. And we can take notions from one to make the other stronger and better and easier to work in. And so that's kind of the happy ending, where we get 2 paradigms that reinforce and complement each other, and we as programmers get more options of ways that it's easy to write code. And of course, it's JavaScript, in this case, that's bringing these two together. It's playing matchmaker between them. Because we got some really cool new features in the last few years in JavaScript that make it easier to work in both of these paradigms. So that's what we're going to be talking about today. OK, that was all prologue, really long prologue. Let's dive in. So Act 1, let's talk about iteration. We said it's machine efficient. Let's see how we can make it more human efficient, more intuitive. All right, we're programmers, so we love trees, right? All programmers just love trees. It's our favorite data structure. Here, I've just got a really, really simple tree. I'm going to have little nodes that are represented by objects, which have a value, and then have a left child and a right child, which might be empty. So it might be a leaf node, or it might just have one. And I've just got a little helper function, make tree here, which is going to take in my simple tree node type and give me a tree that looks like this diagram on the right. So I've just got a few integers in my tree. It's not the most exciting tree in the world. It's a simple tree. All right, now, let's say I want to traverse this tree and get all of the values that are in this tree in order, in a depth first, left to right order, so that they come out in numerical order the way I've arranged them here. If you were going to explain to me, human to human, how one could go about traversing a tree, you might say something like this. OK, you start at the root, the top in this case. Tell me the value of that. And then if it has children on either side, treat each of those like its own tree, and then traverse those. And so for that, you're going to take the value and then look at its children and look at those subtrees and look at the subtrees of their subtrees and the grandchildren, the great-grandchildren, etc. So if you were to explain it to me that way, you'd kind of be talking recursively, right? So one way we might write a function to recurse a tree like this is just with a really simple recursive function. So here I've got a function called recursive traverse, and like any recursive function, it's got 2 cases. It's got a base case, which is what stops us from like falling into infinite dream states and like being Leonardo DiCaprio, like stuck in the dream forever, just falling deeper and deeper. We don't want that to happen, so we need a base case so that eventually something stops and we return. In this case, when we get in a value, we're going to make sure that it's not undefined, that it's not like an empty node that we're looking at. And if it is empty, then we're just going to return. So that's our bottom to the dream state. And then it has a recursive case. So in this case, if there is actually a node here, we're going to log its value, and then we're going to recursively traverse its left child and its right child, which once again might be empty, in which case we'll hit the base case on those recursive calls and pop back out. But if they're not empty, we'll continue going as deep as we need to get all the values out of the tree. So if we run this code, it works. We get all our values out. Yay, wonderful. Great. And I don't know about you, but I find this code pretty intuitive, pretty easy to read and write, because it's kind of how we think about descending a tree in terms of its subtrees. What about an iterative approach to iterating over a simple tree like this? So here's one way we could do it. I've got an iterative traverse function here where basically keeping track of like the nodes that we need to visit in a little to-do list, a little to-do array. And as long as there's stuff that we still need to visit, I'm going to take the thing off of the beginning of that array, make sure that it's not empty, that it's not undefined. And if it is a tree, if it's a node, then I'm going to log its value and then take its left child and put it onto the front of the array, and take its right child and put it onto the back of the array, and then keep going until I run out of nodes to visit. So this code, if I run it, it runs exactly the same. But I don't know about you, but I find this much less intuitive to write in the first case, and also just to read. It's like, all right, we need an array, it's to-dos, and we're like putting things on both ends, like which direction do they need to go, and we're popping things off, and it just doesn't, like, it works, but it's maybe how a computer might think about this code, but it's not how I think about it, how I think about the tree and how we'd want to go through it. So wouldn't it be great, wouldn't we just love to be able to just say, like, for each thing in the tree, tell me what the thing is, and just loop over it really simply in as high level an iterative abstraction as possible? Well, thanks to JavaScript, and notably some of the features that we got in ES6 a couple years ago, we can. Yay! So we got these new iteration protocols. Well, they're not so new anymore, but they're still pretty cool, because before we had those, this was kind of clunky and awkward to work with. But now, thanks to the Iterable protocol, so we can make objects iterable by giving them something that is on the symbol iterator key and returns an iterator. We then, of course, have the notion of iterators, which are objects that have a next method, which returns objects that tell us whether or not there's something else coming. There's like whether or not the series is done. So we've got these iterators that return a series of objects, infinite or finite. And we've got generators to make it really easy to write iterators, because generators are iterators, and they're also iterable, so bonus. So they work really nicely with iteration. We've got this function star keyword to make generator functions. We've got yield to output values from our generator, and we can do that as much as we need to. And then we've got these handy dandy for of loops to iterate over anything that's iterable. So we can define our own iterable things. Like, for example, tree nodes. We could make a tree that's actually, in and of itself, iterable. You can loop over it. So if we were going to make our tree nodes iterable, I'm going to make a new type of node called iterable tree node, because I'm that creative. And we want to give it an iterator that will attach to the symbol iterator property. And I'm going to make the claim that we can actually use our recursive way of thinking about tree traversal to write this iterator. So we're going to build something that I'm going to call a recursive iterator, again, because I'm just so creative with naming. All right, looking back to our recursive code from before, that's what we see on the right here. We had this recursive traverse function. We had our base case, we had our recursive case. I'm just going to shuffle them around a little bit. So now, before we were descending all the way to an empty child. Now we're just going to assume that whatever's coming into this function is an actual tree node. And instead of checking if it's undefined, we're going to move the check so that now we're going to log the value of the node that we've got. And then before we do the recursive calls, we're just going to make sure that they're not, those children that we're about to recurse into are not undefined. So we're just really shuffling things around here. We've still got the same basic approach. It's just we've just moved the check to a little bit earlier so that we don't have to descend all the way to undefined. Now, in this case, our base case is going to be kind of implicit. It's like if we fall through both of the if statements and there are no children, then we just return. And that's kind of our implicit base case here. So my claim is that we can use this recursive code to write an iterator for our tree. What we want to do is we want to have some kind of function that's like this recursive iterator that does the same thing as the recursive traversal function before. It's going to output the value. In the recursive case, it's going to iterate over both of the subtrees. And in the base case, it's just going to finish. It's going to stop. Generators to the rescue. So if we make this little function star, now we've got a generator function. We can basically take the same exact code that we had in our recursive function and turn it into a generator using these yield statements. So instead of console logging the value, I'm yielding it. So I'm outputting it and then pausing there. And then if I have something on the left, I'm going to recursively yield everything from the subtree on the left. So this yield star basically lets us just loop over everything in that subtree. So it's sort of implicit, but it's basically like making a call to the recursive iterator on the subtrees node itself, right? And so really we're using the same concept here to recursively iterate through all of the nodes in this tree. that we were doing with our recursive traversal function, which is a more obviously recursive function. So what we've got now is iterable code that we wrote and we can execute in an iterative fashion using the for of loop, which is super simple and intuitive to write. It's just like, for each thing in the tree, tell me the thing. And it does it. But under the hood, the way it's running is sort of more recursively. So we've got recursive energy, as it were, at the soul of our iterative code. I think that's pretty cool. And it gets even better, right? So now in the 2018, 2019, I think 2018 version of ECMAScript, we're getting like async iterables and iterators, async generators for await of. It makes it even easier to work in the iterative paradigm. And we can still use these kind of like high-level abstractions. We can even have some that are powered by recursion. So pretty sweet, I think. Because what we've got here is we've got the concept of iteration, the paradigm of iteration, combined with a little love from JavaScript and some features over the last few years that have made it easier to work in that paradigm, combined with kind of the approach or the mental model of recursion, gives us iterative code that's much more intuitive to read and write. It's much more human efficient. So I don't know about you, but I think that's pretty cool, and it gives me a warm, fuzzy feeling in my heart. All right, so Act 2, time to talk about recursion. As we said, recursion can often be more human efficient, but machine efficiency or performance is sometimes a problem. So let's look at why that is. Okay, another cool thing about recursion, and between studying philosophy and becoming a programmer, I also studied linguistics because I think languages are super cool. And recursion is also a feature of languages, right? Because we can have sentences, or in this case, a noun phrase, like a dream within a dream within a dream within a dream, where the phrase is sort of building on itself, and it has this nested recursive structure. So we can do that in language, and it's true recursion. Like if you were to analyze the sort of meaning structure or the way it's organized, it really is sort of nested. So we could write a recursive function to output a phrase like this, a noun phrase like this, given a number of kind of dream dives that we want to do. So sort of a depth that we want Leo to like go to in his dream spelunking. So here we've got another recursive function. Of course, it's got a base case. So if we're doing 0 dream dives, then we're just going to return a dream. It's not inside of anything. And otherwise, we're going to decrement the number that we're the number of dives that we're looking for, and make a recursive call to the same function. And then whenever that function returns, we're going to take the result of that and add on within a dream phrase to it. So I've just put this in a little script so I can take in a number at the command line. If I run it in Node, if I tell it I want to do a depth of 3, it's going to give me a dream within a dream within a dream within a dream. So we've got like 3 withins. If I give it 30, I get 30. If I give it 3,000, I get 3,000. It won't even fit on the slides, but you can take my word for it. What happens if I give it 30,000? Ah, yes, I heard somebody say, oh, stack, no, oh. Yeah, we get this sad little error here. Maximum call stack size exceeded. I think in Firefox it even says something like too much recursion. Like too much recursion. Too recursion, much pain. So this is a bummer, because in our minds, like recursion should be able to go on infinitely. There's no abstract, like philosophical reason that recursion can't just continue. And yet, in reality, what we get is we run into this error. JavaScript won't do it. It doesn't like our recursive code. It doesn't want us to have 30,000 dream layers. It's like, no, Leo can't handle it. We're going to break his poor, beautiful little brain. We're not doing it. Heartbroken. This is because call stacks are like a real heartbreaker for recursion. We need call stacks to execute our code, but they don't like recursive code very much. So why is this, or how does this work? What happens when I run this code and I give it the number 3? So I've got my, when my code starts running, I've got a stack. I've got some finite amount of memory that's allocated to like run my code. And on that stack, each time I make a call to a function, it's going to add a new frame. And in that frame, it's going to remember everything it needs to know about the context of that particular call to that function. It's like the scope of that call. Now, the stack doesn't exactly look like what I've written here. It doesn't like look so close to actual JavaScript code. But we're human, so I've written it in a way that sort of helps me understand, okay, this is what the computer is actually thinking about when it tries to execute this particular run of this function with this particular input. So when we call this recursive inception function with 3, we get a new stack frame on top of some of the other global frames and things like that. We get a new stack frame for this call recursive inception with input 3. Now, it doesn't match the base case, so we're not going to do line 5. Instead, we're going to go on line 6, and we're going to say, OK, I need to make a call to recursive inception of 2 so that I can get that result back and then add within a dream to it. So for that call to recursive inception 2, we need a new frame, which is going to make a call to recursive inception 1, which is going to need a new frame, which is going to make a call to recursive inception of 0, which is going to need a new frame. And now here we've hit the base case. So here we don't need to make another recursive call. We don't need to keep adding to the stack. Phew, because we just ran up against the limits of our memory with 3 calls. It's a little bit larger than that in real life. And so we're just going to return the value back from the call to 0. That's going to get returned back to the call to 1. So now it gets the actual value, which is going to add on within a dream, return it back to the call to 2, which is going to return it back to the call to 3, which eventually is going to output our sentence. Cool. OK, now we can probably imagine what's going to happen when we have a number that's a little bit bigger than 3. So if we try this with 30,000, is what happens, right? We start out same limited amount of memory. Now we've got a call to the function with input 30,000. That's going to make a call to input 29,999, which is going to need a new frame, which is going to make a call to the input with 29,998, which is going to need a new frame, which is going to make another call, which is so on and so forth, until eventually we're going to run out of memory and we're not going to be able to fit the next call, the next recursive call, into the stack anymore. And so we get, sad face. We get stack overflow, we get call size stack exceeded, too much recursion, so sad. In any case, it's not fun. So the problem here is that every time as we increase n, as we increase the input to the function, we have to add basically a linear number of stack frames. It increases with the input to the function linearly. Wouldn't it be cool if we didn't have to do that, if we didn't have to add a new frame every time we make a recursive call? Wouldn't we love that? Why, yes, we would. And JavaScript to the rescue. So with an implementation feature called tail call optimization, which is a feature in some JavaScript engines, we'll get back to that asterisk in a moment, we can basically recycle stack frames after a fashion, because we won't need to remember anything about the previous frames on the stack, the previous recursive calls to that function, if we write our code in a particular way where the call to the next function is in tail position. And this gets at this feature called proper tail calls in ES6, which gives us a way to tell if a function is a tail position call or not. And what's a tail position call? What is a tail call, really? So let's take a look. So when we have a recursive function where the recursive call is in tail position, we have a tail recursive function. The recursive function that we wrote before is not tail recursive. So our original recursive inception function, when we make that recursive call, as you can see, it's happening on the second to last line here. Now, I just wrote it that way so it'd be a little bit more clear that it's not the last thing that the function does. But even if we put it on the last line, it's still not the last thing that the function does, because after it makes that call, that recursive call, it has to get the result back, and then it has to do more work. It has to do more computation. In this case, it has to add a string, concatenate a string onto the resulting string from that recursive call. Now, what would a tail recursive version of this function look like? Let's write one. So to make a non-tail recursive function tail recursive, what we can do is use a helper function. The helper function, in this case, I'm going to call it Incept, because as we've seen by now, I am the best namer of things ever. This is the function that's actually going to be recursive here. This is the one that's going to be doing the recursive calls, and we're going to make it a tail recursive function. And from our main function, we're just going to call it, and we're going to pass in whatever number the main function got. So in our not tail recursive function, we had to use all of those layered stack frames to kind of remember where we had been, like remember where we're at in the dive, like how far down we need to go, and so that we can pop back up when we hit the base case. In a tail recursive function, we can't do that, or we don't want to do that, right? We don't want to have all those stack frames. So instead, we need some other way of remembering our history, sort of where we've been. And to do that, we're going to use an accumulator. So in this case, I'm just calling it dreams, and it's going to represent all of the dreams that we've dreamed so far. In this case, if we hit the base case where n is 0, we're just going to return whatever's in the accumulator. And otherwise, we're going to make the recursive call. And in the next recursive call, we're going to pass in the old accumulator with the extra within a dream phrase. And that's going to become the new value for the accumulator. So the accumulator variable helps us remember that history. And when we call the function the first time in our main function, we're just going to pass in our kind of base case as the initial value for the accumulator. So now our recursive call is in tail position, because it's the absolute last thing that the function has to do. It doesn't have to do any more work once it gets the result back. It just has to pass it straight on out. It just returns it. It gets the result from the recursive call and just, phew, sends it on down the pike. So this is the definition of a tail call, or a call being in tail position. It's the absolute last work that the function has to do. Now, when I run my function and I pass in input 3, what happens is a little bit different than before. If I have a tail-optimized JavaScript engine, tail call-optimized JavaScript engine, then what happens when I call tail recursive inception of 3? All right, well, this is going to make a call to incept with inputs 3 and a dream. That's going to get a frame, and that's going to make a call to incept with 2 and a dream within a dream as the accumulator. It's going to add that on. And that's going to need a new frame. But the thing is that when that incept of 2 call returns, again, the incept of 3 call is just going to pass it right on back to the original calling context, to the tail recursive inception function in this case. And so we don't actually need to remember anything about the call to incept of 3. So we can take that stack frame and just throw it out, or better yet, recycle, right? Because we're eco-friendly. So we could reuse the resources, or we could just free them so that we have more space for something else. We basically just take it off the stack, and now our call to incept of 2 becomes the topmost frame on our stack. That's going to make a call to incept of 1. Again, we get a new frame, but we don't need to remember anything about the old one, because it's just going to pass the value right on through, so we can recycle it. And now the incept of 1 call is on the top of the stack. Again, that's going to call incept of 0. We still don't need to remember anything about incept of 1. Incept of 0 becomes on the top of the stack. That's going to return, and it's the base case, so it's just done. No more recursive calls. We get our result back, and we've got a dream within a dream within a dream within a dream. It's hard to remember. So this is how tail call optimization works. In theory, we should be able to get rid of each of those frames as we make a new one, so that we really only need a constant number of stack frames to run our recursive code. So what we've got now is code that we've written recursively, that when JavaScript runs it, when the engine runs it, it's really running it more iteratively. It's running it more like, okay, I just need to remember there's an n value and a dreams value, and they start out being 3 and a dream. And as n goes towards 0, I'm just going to keep adding within a dream to dream value and keep decrementing n. And eventually, n's going to reach 0, and I'm just going to return dreams. So this is sort of how I think JavaScript thinks about our code, is in this iterative way. But we, as humans, think about it in this recursive way, and they both get to play nicely together. Now, this is the dream. What about the reality? How does tail call optimization feel in real life? So now, I've made the claim that with tail call optimization in JavaScript, we should be able to run this code. I've put our function in a little script like before, and I should be able to pass in 30,000 and get out 30,000 layered dreams, right? But if I make this call as written to Node, I still get back the same call stack size error. Did I lie to you? Have I broken your hearts? Have I betrayed you? Well, not really, because I had a disclaimer on my slides earlier, if you remember. I said this was a feature of some JavaScript engines. Yeah, so that's a real big asterisk, because really most implementations of JavaScript don't have tail call optimization. Only a couple really do, so WebKit is one, and V8 Chrome node had it, but got rid of it because of some issues. And really, this is actually a whole wormhole if you want to do some Leo style, like diving into the arguments behind tail call optimization, whether or not it's a good idea. Like, be my guest. There's plenty of debate going on. There's some of the problems with tail call optimization or implementing it in JavaScript are laid out in a cool blog post from the V8 team. And this discussion is still ongoing. So like there's a proposal out for making like explicit tail call syntax to solve some of the issues that came up. And there's also proposals like in the WebAssembly community to talk about getting tail calls in there. So you can check out the slides later. I'll put them up, and you can read all about this. But suffice it to say, this is a hotly contested feature. But I said that V8 and Node kind of used to have it. So if we use Node 6, and in this case I'm using NVM to make sure that I'm using Node 6, and if I pass in the right flag, so Harmony tail calls flag or just Harmony, now if I run my function with 30,000 as the input, it works. OK, now you can try it yourself if you don't believe me. And this is obviously not 30,000 because they definitely don't fit on a slide. But the point is that with this feature of tail call optimization, which I have to jump through some hoops to enable, but it is eventually there, we get our limitless, essentially, recursion that we wanted. So my point has been, and I'm sorry I'm over time a little bit, but my point has been that now we've got code that we wrote recursively, which thanks to some features of proper tail calls and tail call optimization in JavaScript engines, lets us execute that code in a more iterative way. So we get more machine efficient recursion. So I can think as a human in recursion and execute it as a machine iteratively. OK, so this has basically been the point. We've got these two competing paradigms that are ostensibly like in this epic feud forever. They hate each other. But really, with some love from JavaScript, we've seen that they can sort of complement each other and reinforce each other and make both of them easier to work with. So we as programmers have more choices, and we can decide what the best tool is for the job, which paradigm makes more sense for us to work in. And this is really the goal, I think, is for us to, as we advance like the state of the art as programmers, to get more options and have more ways of easily writing and efficiently running code. So if you want some further reading, there's plenty of it. You can check out the slides later. That's it for me. Mulțumesc!